Right, hello everybody. I am hoping this is going to work. I am not very good at anything technological, so you'll have to bear with me. Right, anyway, here we go. So I am hoping that you are all okay and that you can see this all right. I didn't want you to have to do the next couple of lessons by yourself without my help, so I am going to attempt to video myself teaching you this. We'll see how this gets on. Right, first of all, welcome back. So long since I've seen you, for 5 weeks maybe since I've seen any of you at all. I have been really unwell. I am still far from well, but I am slowly making progress towards being better. I hope that all of you kept well. If you did get this horrible virus, that it treated you well and your families as well. Do let me know if you're struggling, and I will be perfectly understanding of you not being able to do your work. Right, we have got a couple of lessons left before we have finished all of year 12 content for chemistry, which is good news. And I think that it's a difficult thing for you to do by yourselves with just the PowerPoint. So I really wanted to try and do this. So we have only got about 3 more lessons left that we need to do. We are hoping that we may be back to school after May half term. I think it's unlikely before then, but with a bit of luck, maybe by then. But obviously that leaves us with, 7 weeks of work. So we'll try and do it this way. And hopefully this will be helpful for you. If you could please get up the PowerPoint that I send with this video, that would be really helpful for you to go through the PowerPoint as I'm talking about it. And because of that, I am going to switch my video camera around and point it at the PowerPoint so that you can follow along as we're doing this. Okay, so here we go. Right, so this is an infrared spectrum, okay? And so today's topic is all about infrared spectroscopy. It's a way of us being able to identify chemicals that we don't know. We use it in forensic science, in various other areas of life. And it's a little bit like a fingerprint. Each individual chemical has its own individual infrared spectrum. So this is what the specification says. You need to know what infrared spectroscopy is, how it's useful. It causes the covalent bonds to vibrate. Each individual bond will have a different wavelength of radiation that it absorbs, and so therefore each individual organic compound will have a completely unique spectrum. You need to know 4 in total. Okay, here we go. You need to know this one, an OH bond. You need to know this one, the C double bond O bond in an aldehyde or a ketone. You then need to know how it's different in a carboxylic acid, and also the OH bond in a carboxylic acid as opposed to a alcohol. And then you need to be able to use an infrared spectrum that you've given to be able to hopefully identify, or use partly to identify an unfamiliar sum. And then this last little bit's important for you to know. You need to be aware of how we use it. So we use infrared spectroscopy in air pollution, working out how much carbon monoxide and nitrogen monoxide there is in the air, breathalyzers to measure alcohol, and so on. Okay, right, do you all remember electromagnetic spectrum from physics, hopefully, GCSE physics? So you'll remember that in the middle here, if you've got your visible light, and then so getting longer wavelength, here we go, it's coming down, we've got infrared spectrum here, which is the one we're using today. Then we've got microwave, then we've got radio waves coming all the way down here. Getting shorter is obviously the ultraviolet, the X-rays, and then the gamma rays coming up here. So we're going to be using this infrared section of the electromagnetic spectrum. So each bond in a molecule will absorb a unique wavelength of, or unique frequency. Remember, wavelength and frequency are related to one another. In fact, if you go back there, as wavelength gets bigger, frequency gets, so wavelength gets bigger, frequency get bigger too. I am not a physicist. Hopefully you can work that one out. So here's wavelength is getting bigger. So frequency, I thought frequency got shorter, but maybe it doesn't. You can work that one out. Anyway, it doesn't matter for chemistry. All right, so here we go. We've got, oh, that's right. So frequency and wavelength must be, the bigger the wavelength, the longer the wavelength, the less the frequency is, surely, because you can't fit as many waves. You can't fit as many waves in. Hang on a minute, I'm going to have to draw this one out. Okay, so here we go. So here's my wavelength, like this, top of one wave to the top of the next wave. Yeah, that's my wavelength. Yep, everybody happy with that one? Frequency is how many cycles I can fit into a second. So therefore, if I've got a longer wavelength, I'm going to have less frequency. Is that correct? Hopefully, physicists amongst you will be able to work that one out. It doesn't actually matter for what we're talking about today. The important bit for you to know is that each bond vibrates at its own unique frequency. So you know, like how like if a lorry goes past your windows and it makes them vibrate, that's because the frequency of the lorry's sound matches your window, and that's what makes it vibrate. So if we've got the correct wavelength coming past a molecule, each individual bond within it will vibrate at its own unique frequency, and that depends on the strength of the bond, the length of the bond, and the mass of the atoms involved in the bonding. And so what we do is we kind of get a situation where you have a little container like this, and you put your sample in that you want, and then you shine a light through the sample like this, and then it comes out the other end, and you have a detector over here. So you've got your detector over here like this, and as you shine the light through, you change the frequency or the wavelength of your infrared radiation. And if there's something in here that absorbs that particular frequency, then you'll get less of it coming through here, and you won't get any detected over here. If there isn't, if it's not absorbed by there, then it will go straight through and be able to be detected. Does that make sense? So what we're actually measuring is whether the particular frequency has been absorbed or not. Okay, so what you get, can you see that? So what you get, this is 100% up here. So that means if everything passed through, not absorbed at all, you get a line going at the top here. Okay, so this is your wave number, which is 1 over wavelength. Okay, so as your wave number, this is decreasing. So as your wave length increases effectively. So as you can you see that? Gosh, let me just draw the curtain behind that, and then that might shut out the light. Is that better? There you go. Hopefully you can see it on your own PowerPoint. Okay. So as your wavelength increases, or your wave number decreases, what happens is that most of the time, that particular, let's see if I can get that, oh gosh, I'm not very good at this videoing business, never mind. There we go. So most of the time you can see that, hang on, if I move my arm away, it works. Okay, there we go. So if you see like there, that most of it is passing through, you know, you've got what about that, what's that, 70, 80, 82% passing through. And then you get these spikes or these troughs, okay, peaks, troughs, where at that point, obviously that particular wave number, inverse wavelength of infrared radiation, has been absorbed by the sample. And so virtually all of it has been absorbed and very little of it passes through to my detector over here. So that means that at that particular wavelength, my sample has absorbed it all and very little of it is able to pass through. So you get these kind of like these little peaks like this going through. You see them? All right. So that's what your like little spectrum looks like when you've passed it through the infrared spectrum. Well, hopefully I can get this done. Now, the bit towards the right is very complicated. We call that the fingerprint region. It's unique for each individual molecule, but we don't need to know about it at A level, okay? It's very complicated to be able to analyse. So what we are looking at is the left-hand side, okay? Now, these are the absorptions you need to know. If you look at your data sheet, which you should all have a copy of, if you don't have a copy of, email it me and I will send you a digital copy of it. It's the one that's either, I don't know what colour I did for you, bright orange or bright yellow, purple. Can't remember what colour yours are. I've done various colours. I try and find a bright colour to give you one. But anyway, there you go. So it should be on there. So these are the wave, oh gosh, sorry about that. Every time I put my hand in front, it messes things up. See if I can try it with a pencil. There we go. Maybe if we do that. Hang on, let's get it. There we are. So look, here we go. Here's your wave numbers. So these are the numbers that are along the bottom. You see these ones, these numbers here along the bottom? Okay. And these are the bonds that are attached to that particular absorption. So here's a carbon-oxygen, carbon-oxygen double bond, carbon-hydrogen, an OH in a carboxylic acid. Don't need to worry too much about that one. We'll do that next year. And an OH in an alcohol. Okay? So that's what we're looking for. Now you might think, oh, that's a bit complicated, but don't worry, it's much easier than it looks. Okay, so if we look at this, okay, so the ones that you need to know, and the specification asks you to do about alcohols, carbonyls, those are aldehydes and ketones, and carboxylic acids. I've thrown in alkenes for just for free as an extra bit of fun. Okay, so these are the troughs or peaks that we are looking for, and they're these numbers that we're looking for them. So in an alcohol, obviously, you've got an OH, you've also got some CHs, but you don't have any C double bond O's, or you do have a C single bond O, okay? So hopefully, there we go, you can see that. So you've got an OH, some CH, and then a CO, but we shouldn't see this one. For a carbonyl, you've got some CHs and you've got C double bond O's. Remember, this is aldehydes and ketones. You don't have any OHs or C single bond O's. Carboxylic acid, you've got a bit of each, because remember, your carboxylic acid, just for a little reminder, refresh your memory, carboxylic acid is a C double bond O bond OH, like that. So you've got a C, so here we go, look down there, see, you've got a C bond, single bond O, a C double bond O, and an OH. And obviously you'll also have, because even if it's methanoic acid, you'll also have some CH in there. So with carboxylic acids, you can see that you've got all of those. And then alkenes, really boring ones, have only got CHs and nothing else in there at all. So we're going to look at each one of those in turn. I'm going to start with the alcohols. Now, I have put also attached a whole series of the spectrum, which you can print out and put in your notes. And you might want to kind of go through those as we look at these, and you can actually annotate what we're looking for. So with alcohols, remember, we're looking for an OH somewhere between 3,000 and 3,300. We're looking for some CHs at 2,850 to 3,100. And we're looking for a C single bond O somewhere between 1,000 and 1,300. Okay, now, sounds dreadfully complicated. It is not. let's have a look at some. Now what I'm going to do is I'm going to scroll through quickly. These are all alcohols. I want you to particularly concentrate on the left-hand side of the spectrum. So as I scroll through, here's one, here's another one, here's another one, here's another one, here's another one. One more. Let's go back, okay? Right, what are you noticing? Can you see that at the left-hand side, oops, oh God, I went too far. At the left-hand side, as I scroll through, can you see that actually you get the same shape each time you look at the spectrum? So let me show you, here's a typical one right here, okay? So, whoa, hand goes in the way. Let me swap hands, see if that improves the situation. I'm just not very good at this videoing business. Here we go. Right, so can you see that what I call this a double dip? You have a dip coming down here, which is due to the oxygen-hydrogen bond. If you look at the numbers, if we zoom in on that, that is at about 3,000, that's 100, 200, 300. So that's about 3,350, yeah? Somewhere around there, 3,350. So that, let's just quickly go back to my one where, there we are. See, look? So somewhere between 3,000 and 3,300. So you've got an OH there, okay? So let's go on, there we are. And so, look, there we are, there's another one right there. So that is, again, if I zoom in, 300, 3,100, 3,200, 3,300. So about 3,300, you've got this OH due to an alcohol. And then you've always got this, like this has always got a little jagged bit on the end. This is your carbon-hydrogen absorption, just here. And that's at about, I don't know, 2,900, something like that. So again, if I scroll back, so your CH should be between 2,850 and 3,100. So that's what we're seeing there. So with an alcohol, you always get this double dip. The first peak due to the OH, and then the second peak due to the CH. You also should have one somewhere around about 1,000, well, this one's coming up at about 1,450, something like that. Okay, so here we are, somewhere between 1,000 and 1,300, you should get another dip like that. That one's a bit further over. Okay, so this one here. So it'll be one of these somewhere around here. You don't need to worry exactly which one it is. Probably that one there for that particular one. Okay, so but you can see again, you've got this what I call a double dip. First one is smooth, second one's jagged. First one is smooth, second one's jagged. First one is smooth, second one's jagged, and so on. They're always in the same places. So can you actually see that is what you are looking for when you're looking for an alcohol? Okay, that double dip at the beginning, smooth first peak, second jagged peak, like that. Okay, so there you go, alcohols. So that one's easy. Aldehydes and ketones, again, have a look as I scroll through them and see what you can notice about this one. Let me get the camera in the right place. Can I do that? No, there we are, that's a bit better. There we go, right, try that one. Right, so this time we're looking for a CH, that jagged bit at the beginning, but no OH this time. And then we're looking for a C double bond O between 1,840 and 1,750. Now, if you gain, it sounds complicated, it's not. Just have a look, see what they look like as I scroll through them all. Let's go. So look. Right, can you see? Ooh, that wasn't many of those. Right, so let's go backwards and forwards. Can you concentrate on the middle of your spectrum? Can you see that big peak in the middle? That's your C double bond O peak. Okay, so let me have a look at that one. So that's this one here. Whoa. Okay, let's see if I can zoom in on it. Right, here we are. Look. So you've got that's 1,500 and 1,500. So it's 1,600, 1,700. So that's around about 1,720, something like that. So you can see that one. That is your C double bond O. You've also got your jagged carbon hydrogen around here, around about the 3,000 mark as well. So if we have a look at the next one, again, you can see, again, this big peak in the middle, around about 1,700. It kind of cuts your spectrum in half. So you're looking for the big peak in the middle, and then your little jagged one around about 3,000. So we look again at the next one, again, big peak in the middle, around about 1,700 and something. And then you've got your jagged ones around about 3,000 for your carbon hydrogens. So what you're looking for alcohol, remember, you're looking for the double dip at the beginning on the left-hand side. For an aldehyde or a ketone, your carbonyl, you're looking for that big dip, kind of like cutting your spectrum in half. Okay, and no double dip at the beginning. Okay, right, on to carboxylic acid. Carboxylic acids are the easiest ones. They have this very broad trough between 2,500 and 3,550. Now, if you look at the carbon hydrogen numbers, that's between 2,850 and 3,100. Can you see that that kind of sits in the middle of this? So what happens is that this actually swallows up the carbon hydrogen peak. So what you end up with is this really broad peak that swallows up the carbon hydrogen peak. So you don't go in a double dip, you get kind of one trough because these two kind of merge into one another. You then get that carbon-oxygen double bond, which kind of cuts your spectrum in half, and then you get your carbon-oxygen single, which is over to the right-hand side. It's not so obvious. Right, let's have a look, see what those look like then. So here's your carboxylic acid. Can you see that really double, that massive, great, big thing at the beginning? Look. Oh, every time I do it with that hand, it kind of messes my thing up. There we go, let's try this. So here we go, look. Here's your really broad, so you've not got a double dip this time, it's kind of swallowed up that carbon hydrogen. You always get this little rough bit here because it's swallowed up the carbon hydrogen. And you've got this big peak in the middle, cutting your spectrum in half. This is like distinctive for carboxylic acid, okay? Right, here we go, there's another one. See, look, broad trough at the beginning, and then the one that cuts the spectrum in half. There's the next one. There's another one, not quite so broad, that one isn't. And there we go. Okay, so this is really distinctive. So alcohol, double dip. Aldehyde and ketone, just this one in the middle, but you've not got that one over there. And then carboxylic acid, you've got this really broad thing like this. Okay, right. Alkenes I'm throwing in for free. Okay, it's not in the specification. You obviously haven't got any of those things. So these ones look really simple. You've basically got your carbon hydrogens here. There is a little tiny carbon double bond over there, but that's it. So what you're looking for with this one, whoa, no double dip, no big broad thing at the beginning, nothing cutting your spectrum in half in the middle. This is an alkene. Okay, there we go. You've just got the jagged. Can you see that's just the jagged one for your carbon hydrogens over there? Okay. Right, so you should also have your, if you can print them out, fantastic. The ones that I send with this, which is lots and lots of them, make some notes. Hang on a minute, where am I doing there? Make some notes on how you recognise each functional group and what the key peaks are and what wave numbers you find them at. Okay, so there we go. Right, so obviously I'm hoping you'll recognise them. I'm going to pause for a second. You can shout out what you think they are and then I'll tell you whether you're right. Okay, here's the first one. Did you get that right? Double dip at the beginning, that's an alcohol. Right, shout it out. Here's the next one. Right, nothing at the beginning, but you've got this big peak in the middle. So that's either an aldehyde or a ketone. Okay, next one. Right, really boring here, just your carbon hydrogens. That's an alkene. What about that one? Do you get that one? That's a carboxylic acid. It's swallowed up your carbon hydrogen here and it's got the big peak in the middle. Okay, what about that one? Yes, that's an alcohol. Double dip, down, up, down, up. Okay, it's not broad enough to have the... I'm wondering whether that one is actually, because you have got your peak in the middle there. I wonder what that one is. Ooh, but it is a double dip, so that one might be an interesting one. That one I think may well be slightly more complicated, and you might have there, because you've got a double dip for definite sure, so that's an alcohol, not a carboxylic acid. But you do have this little one in the middle here, which is about the right one for a C double. So you may have a ketone or an aldehyde somewhere else in the structure. So that one's quite an interesting one, actually. Right, what about, oh, there we go. Okay, I am going to also put up on Show My Homework some past paper questions on infrared spectroscopy. I will put the mark scheme up with it, so please do try to do it without looking at the mark scheme to start with. Hang on a minute. And then could you mark your own? And this week, I really would like you to send me what score you got in those past paper questions. Okay, so have a go at that for me. Do remember that each week I'm also going to have question and answer sessions during our normal double period slot. So not the single period, but the double period. When you would normally have a double period with me, I will be available on Microsoft Teams to answer any questions that you might have. Okay? Anyways, I'm glad we could do this. I will be doing the next one on mass spectroscopy when I can figure out how to do the video link. Okay? All right, take care and talk to you soon. Bye.